We'll now learn how to calculate the heading we must fly to make good a desired track, and the ground speed which will be achieved along that track. This is by far the most frequent navigation exercise carried out by private pilots when planning a cross-country flight. We know what track we wish to fly because we've drawn a line on our map from our airfield of departure to our destination. We'll assume that we wish to fly from Nether Hayford to Rissington Parva. We measure the track to be 240 degrees true. We elect to fly at an indicated airspeed which gives us a true airspeed of 110 knots at our chosen cruising altitude. And the wind is given as 270 degrees true at 25 knots. First of all, let's look at the triangle of velocities for this type of calculation, so that we can visualize the problem. Because we know that the wind direction we've obtained is in degrees true, we'll decide to stay with degrees true just for the moment. Our line on the map can be used as the first line of our triangle of velocities. Note, however, that the track line gives only the direction of the ground vector of our triangle of velocities. We don't yet know its length, because that will give us our ground speed. The triangle of velocities deals with directions and speeds only, not distances, so the distance between Nether Hayford and Rissington Parva is irrelevant to our calculations. Remember, we're now dealing with a vector triangle, not with lines drawn on a map. Because we know the speed and direction of the wind, we also know the direction and the length of the wind vector. As pilots, we immediately deduce that we shall have to fly a heading right of track to compensate for drift. We thus draw the wind vector at the head of the ground vector, having chosen a scale for the speed, say 10 knots equals half an inch, although any suitable scale would do. All that remains for us to do now to complete the triangle of velocities is to draw in the air vector. Let's assume that we've chosen to fly at an indicated airspeed which gives us a true airspeed of 110 knots at our chosen cruising altitude. Thus, while we don't yet know the direction of our air vector, which will give us our heading, we do know its length. Its length will be 5½ inches, or 140 millimeters. We can set this length on a geometrical compass. Place the point of the compass at the open end of the wind vector and draw an arc intersecting the ground vector. We join this point of intersection to the open end of the wind vector to give us our air vector. We've now completed the triangle of velocities and have obtained a direction and speed for all three vectors. The wind vector, of course, we already knew. We now, though, have a direction for the air vector of 247 degrees true. This gives us the heading we must fly to achieve our desired track, as well as showing our true airspeed by its length. The ground vector now has a length from which we measure our ground speed. Or, in other words, the speed achieved along track. In our case, this is 87 knots. So our problem is solved. To make good a track of 240 degrees true, with a prevailing wind from 270 degrees true at 25 knots, an aircraft flying at a true airspeed of 110 knots will need to fly a heading of 247 degrees true, and will achieve a ground speed along track of 87 knots. Of course, as our compass or direction indicator gives us our heading relative to magnetic north, we need to adjust our calculated heading for magnetic variation in order to find the compass heading to steer. For example, if the magnetic variation were 5 degrees west, we would add 5 degrees to our calculated heading and steer 252 degrees magnetic. The angle between the ground vector and the air vector shows the amount of drift the aircraft is experiencing. In this case, 7 degrees to port. In our diagram, in order to make good its track of 240 degrees true, the aircraft has corrected for that drift by heading 7 degrees into wind, and by flying a heading of 247 degrees true. For this reason, the angle is also known as the wind correction angle. The wind face of the flight computer solves triangle velocities problems for you. We'll now show you how this is done. In this example, we plan to fly a track of 231 degrees true at a true airspeed of 100 knots with a forecast wind of 110 degrees at 20 knots. On the wind face of your navigation computer, rotate the inner scale and set the wind direction of 110 degrees against the index mark. Now adjust the slide to put a thick speed arc under the center circle. Here we've chosen the 80-knot arc, but we could have chosen any thick arc. Mark a cross on the center line of the slide, down from the center circle, at a distance representing 20 knots wind speed. In this instance, the mark must be made where the center line intersects the 60-knot position. What we've just done is to mark the length of the wind vector. Move the slide so that the arc representing our true airspeed of 100 knots is under the center circle. We set the true airspeed under the center circle because, as you'll see, the center line of the slide below the circle becomes the air vector of the triangle of velocities. Now rotate the inner scale to set the desired track of 231 degrees against the index mark. Note that the wind vector is now oriented correctly, as in the complete triangle of velocities which you can see in the inset. The drift line of the slide, below the wind mark, now actually gives us our ground vector. When we finish the calculation, the wind mark will therefore give us our ground speed. Note that the wind mark is now nearest to the 9-degree drift line to the right of the center line, indicating that we have 9 degrees starboard drift. In this case, the computer is telling us then that we have to head 9 degrees to port to achieve our desired track. Initially, rotate the window disk to align our notional heading under the index mark. That's 231 degrees minus 9 degrees equals 222 degrees. You'll notice that the wind mark has now moved nearer to the 10-degree starboard drift line, due to the movement of the window disk. Because of this, we have to adjust the window again, to take account of this new drift of 10 degrees starboard. Rotate the window to put 221 degrees under the index. You'll see that the wind mark remains on the 10-degree drift line. The drift on the fixed scale against the track of 231 degrees is the same as the drift under the wind mark, 10 degrees. This tells us that the notional heading of 221 degrees that we've just set against the index mark is the actual heading we need to steer to achieve a track of 231 degrees. The ground speed of 108 knots can now be read off from the speed arc which passes underneath the wind mark. Again, in order to find the heading to steer on your compass, don't forget to add or subtract the local magnetic variation. Let's try another example. This time, though, we won't draw the triangle velocities onto the wind face of the computer. We'll do the calculation as you'll probably do it during your flight planning. We'll assume that we've planned a flight from Oxford to Harden via Ludlow. The wind for the whole route is given as 070 degrees true at 20 knots. Our true airspeed will be 103 knots. We need to calculate our heading and ground speed for both legs. First, we'll put the wind mark on the window. Rotate the inner scale and set the wind direction of 070 degrees against the index mark. Adjust the slide so as to put a thick speed arc under the center circle. Mark a cross on the center line of the slide, down from the center circle, at a distance representing the wind speed of 20 knots. Now adjust the slide to put the true airspeed of 103 knots under the center circle. Rotate the inner scale to set the desired track of 302 degrees against the index mark. Note that the wind mark is now over the 8-degree drift line to the left of the center line. Remember, this shows us that we're expecting port drift, so we'll have to head starboard, or right, to counteract that drift and achieve our desired track. Add 8 degrees to the required track, which will give you a notional heading of 310 degrees. Then move the window to put 310 degrees against the index mark. You'll notice that the wind mark has now moved onto the 9-degree drift line. Reposition the window to take account of the extra 1 degree of drift, that is, put 311 degrees against the index mark. You'll notice that the amount of drift does not change when you move the window. This amount of drift, when applied to your track, will give you the heading to fly for the required track. Read off the heading to steer of 311 degrees against the index mark. Note that our track of 302 degrees appears under the 9 degrees port drift mark on the top scale. This confirms that the drift we are applying is correct. Read off the ground speed of 114 knots from the speed arc which cuts under the wind mark. We've now calculated our heading and ground speed for the leg Oxford to Ludlow. Of course, you'll apply the local magnetic variation to find the heading to steer on your compass or direction indicator. Now we'll work out the heading and ground speed for the second leg. Leave the wind mark and the slide position as they are. Just rotate the window to put the second leg track of 349 degrees under the index. This time the wind mark moves to the 11-degree drift line to the left of the center line. Remember, this is drift to port. Add that amount of drift to the required track, which will give you a notional heading of 360 degrees. Then move the window to put 360 degrees against the index mark. You'll notice that, though you've moved the window, the wind mark remains nearest to the 11-degree port drift line. Thus, 360 degrees is the heading we must fly to achieve the required track of 349 degrees. As a check, you can see from the drift scale that our required track of 349 degrees appears next to the 11-degree port drift line. Read off the ground speed, 98 knots, from the speed arc which cuts under the wind mark. Once again, don't forget to apply the local magnetic variation to the calculated heading to determine the course to steer on your compass or direction indicator. We've now calculated the heading and ground speed for both legs of our flight from Oxford to Harden.